with health, human health, like blood level. You can see in this map the distribution of lead. There is for pet sampling, we collected 72 sampling and analyzed this by using ICP and apply some interpolation surface, and we find this distribution of lead is related with direction of wind in this area. And we as well, we apply two kinds of analysis, chemical analysis, which is find variety of lead contamination, as well variety of physical and chemical characterized. Then we apply some analysis spectrometer by using two different kinds of spectrometer, and we got this curve with different concentration of lead. In initial conclusion, the signature of lead was very low, so we need to improve this result by apply some technique like first derivative or second derivative. Then we have opportunity to build modeling concentration by then apply some correlation and prediction. Thank you for your attention.
Thank you. As I mentioned, question directed to the presenter of the session that is open afterwards.
Thank you. Next presentation is given by myself, and the title of the presentation is Soil Spectral Imaging, Moving from Proximal Sensing to Spatial Quantitative Domain. So if this is a poster, it needs to be fitted on one page. So usually what we are doing today with soil proximing is taking the soil spectra and estimating soil attributes. And there are lots of works that are done within this discipline. And what we do, we take the spectrometer measurement of the soil, we take chemical analysis traditionally, and we find a model, and the model predicts pixel by pixel the soil attributes, and we can apply it on the surface to each of the pixels. And the question, of course, can we do it to map soil? And the answer, although we have very, very promising results, no. And you see that the mapping, the soil mapping, is not possible yet. And what are the problems? The problems are quite few. First of all, we are missing a signature of reflectance from hyperspectral remote sensing. We are getting atmospheric attenuation, we need to remove them. And if we are looking at very tiny little spectral features, if we are not doing this correctly, then we can kill the analysis. Then the high cost of hyperspectral remote sensing missions. The signal to noise within the aircraft, the sensor that airborne is pretty low. We have the BRDF effect. And then we have crust on the surface. We don't see the entire soil. We see just the 50 first micrometer. There can be crust, there can be dust, there can be lots of things like humidity. And the most important thing, we don't see the profile. And to map soil, you need to have description of the profile. And of course, in the end, if you would like to find a model for spectral information, you have to use lots of data resources, lots of computer resources, and a lot of experience. What are the solutions? For the radiometric and atmospheric calibration, you need to do vicarious calibration. There's no doubt about that today. Now we are going from big airplane to UMVs. The signal to noise is improving because the technology is improving, so very soon we're going to have the same SNR as we have in the laboratory. We now have some methods to correct for the BRDF. The soil crust, in terms of physical crust and biogenic crust, can be modeled today. And we have found some very nice tool to measure the soil profile spectrally with what we call pulse-penetrated optical sensor. And the computing is getting very progress today, and we have developed a program called Barracuda. When you put your spectral in one side, your data chemical in the other side, you put it into the machine and you get the best model out of this machine. You don't have to know statistics, you don't have to be expert, and in the end you get very good model. If we do all this, we can in the end go and map soil. So thank you for your attention. The next presentation is given by Glenn Newham from, yes, but the other one is here. This one? Sorry, okay, sorry for that. I thought it didn't come up, but okay, so the third one is from Professor Jean-Duc Lee, is that correct? Okay, from Hyumak National Institute of Technology, Korea. The title of his presentation is Analysis of Concrete Reflectance Characteristic using Spectral and Very Near Hyperspectral Sensing. You should be in the other oral presentation though, is not the case? We're waiting for you. Waiting for
you. This research purpose is to extract spectral reflectance of concrete through basic experiment on concrete specimens and side experiment on actual concrete structure. We used two types of hyperspectral sensors. Field portable spectrometer named GER3700 and VNIR hyperspectral camera. This graph shows spectral reflectance of concrete according to wavelengths extracted by spectrometer GER3700. Or super high strength concrete graph shows very differently with other 8 concrete, general concrete. We photographs 4 different specimens together with 99%, 75%, 50%, and second 2% reflectance panels by VNIR camera. This graph shows spectral reflectance according to wavelengths, four different strengths concrete and four different reflectance panels. Reflectances were computed by dividing into 99% reflectance panels. And then we performed the experiment on actual concrete structure, such as bridge, slab, and pier. We used two types of hyperspectral sensors. Upper ones by GER 3700 and lower ones by VNIR camera. Conclusively, field of portable spectrometer data as well as VNIR hyperspectral images are very useful as reference data in analyzing for maintenance of concrete-based structure using airborne or satellite hyperspectral images.
Thank you.
Okay, now the next paper is by Glenn. Title of his talk is Assessing the Importance of Hyperion Spectral Bands for Fraud Classification. Glenn comes from CCIO, Land and Water Division.
I didn't expect my talk on one slide. I didn't way too many slides, but I ran through. So this work is part of a large project called the International Forest Carbon Initiative. And this small component of it was looking at whether we could move past the current Australian National Carbon Accounting System situation where we divide the landscape into forest and non-forest. And we're looking at if you could use hyperspectral data to classify more detailed forest types. One of the methods that we looked at was random forests. And random forest is a very strong classification method that performs very well. But something that came out of the work was these importance measures, which are a byproduct of the random forest method. So I just wanted to show you some of those, and you can come and chat to me after the session if they seem of interest. So for a dry eucalyptus class, the black line here shows importance measures over the full spectrum, and in black, and in green there's just a spectrometer measurement of a eucalyptus leaf, just as a reference. So you can see there that the important bands from a Hyperion perspective, if you're trying to classify dry eucalyptus forest, are in that blue-green region and in the red. And across the shortwave infrared, there's pretty much nothing there. To contrast that with a non-forest class, this is basically grassland and pasture, there's a really strong feature around about the 700 nanometer region, and less importance in the visible. These are all the importance curves for the classes that we were interested in, and you can see there's a bit of clustering down at the short wavelength end there. So those peaks that coincide are all our individual forest classes, so there's a lot of similarity there, but the non-forest class really sticks out. So I guess the question is, how do you use this information in some sort of operational system like if you do carbon accounting? And one potential way of using it is to look at these importance curves and say pick a narrow band at the peak of each of the importance features and base some more operational statistical method on those that subset of bands, so say linear discriminant analysis. Something we were interested in was the relationship between the overall importance for a full statistical model for the classification relative to broadband sensors. So this is the model importance curve in black relative to thematic mapper bands. And you can see that the thematic mapper bands match up fairly well with the importance peaks there. Comparing that to modus bands, the modus bands tend to fall just off those peaks. So, you know, based on that sort of information, you might select just, if you're basing it purely spectrally, you might decide that T might be the way to go. But there's a lot more potential applications in those importance curves, and I'll be happy to chat to anyone about those after the session.
Yeah, that's the wrong way. Yeah. And the next one here? This one?
Okay, sorry for that. We have sometimes technical problems. This is natural. So the next paper, I hope it's worth it, is given by Vijas. Is from, I cannot read it, I'm sorry. So you, okay, you tell yourself where you are. And the title of his talk, Anomaly Detection and Comparative Analysis of Hydrothermal Alteration Material through Hyperspectral Multispectral Data in the Turriamba Volcano.
Thank you for the introduction. Good afternoon, sorry. The topic of our work is the study of the spectral anomalies and hydrothermal alterations using image spectrometry. I'm going to talk briefly about a multi-source approach in the Turrialba volcano complex, currently active, located in the central volcanic range in Costa Rica. For this work, we used data from HIMAC, master and aster sensors. The airborne images had been atmospherically corrected by an empirical method based on field radiometry and also georeferenced directory using an inertial GPS immune system. Image exploratory techniques had been applied with the aim to contrast biophysical parameters and obtain a first approximation of the state of vegetation and soils in the Turrialba region. We can see some examples from HIMAP data. Let's turn now to the methodology of hydrothermal alteration detection. We have chosen 4 variables for generating a different PCA, 2 highly reflective and 2 highly absorptive for each mineral. We analyzed clay-filled minerals and iron minerals. The results are strongly influenced by vegetation cover. A good example of this is the core composite for minerals we can see in these pictures. Anomalies obtained for red and cyan algorithm had been verified by a method based on projection pursuit and thermal index, only for the master case. We can see some examples of spectral anomalies for the Turrialba crater and for man-made materials. The relations between spectral anomalies and hydrothermal alterations has been studied. Anomalies and hydrothermal alterations detected from high map in Turrialba and surrounding areas is linked to crops and bare soil, as well as to man-made surfaces, roofs of buildings mainly, and varied remains. Some conclusions. It has been found that the higher spectral resolution of the images improves accuracy in the detection of diagnostic bands of the hydrothermal alteration minerals analyzed. higher concentration of hydrothermal alteration minerals in the scenarios where the sources of error, mainly vegetation, are minimized, are correlated with the anomalies calculated in the reflective spectral range. A clear relationship has not been established